Good evening, everybody. Welcome back to the Bar at the Edge of the Universe. I am your host, Adrian D. Maddox, and tonight we are going to be examining another answer to the Fermi paradox, one that is, in my opinion, the most pessimistic answer to the Fermi paradox, the rare earth hypothesis. In a nutshell, the rare earth hypothesis says that humans are alone in the universe. And that's not ideal, in my opinion anyway. I guess one way you could look at it if we are alone is that the universe is ours. Like, it's our playground and we can do what we want with it. But the idea that in the entire universe we could be potentially all alone, I don't know, that's scary to me. I don't really like that. That's not my idea of a perfect reality, I suppose. But nonetheless, the rare earth hypothesis does have many valid points. And the more I dug into it, I wouldn't say that I believe it 100%, but I definitely think that it is probably up there with one of the more likely answers to the Fermi paradox. So the rare earth hypothesis originates from a book called Rare Earth: Why Complex Life is Uncommon in the Universe. This book was published in 2002, and it's by two authors, Peter Ward, who is a geologist and paleontologist, and Donald E. Brownlee, who is an astronomer and astrobiologist, and they were both faculty members at the University of Washington. In this book, they examine several key factors that could potentially play a large role in the evolution of complex life on Earth. And they propose the idea that these key factors are pretty rare to find in other places in the galaxy or other places in the universe, and they're not likely to be repeated very often, if at all. So if we look back at the Fermi paradox, which is the contradiction between seemingly high likelihood for intelligent life or complex life and an apparent lack of any evidence, this kind of takes the first part of that completely out of it. So the seemingly high likelihood, well, the rare earth hypothesis says that no, there is no high likelihood at all. It's a very small likelihood, so therefore there's no paradox. And they touch on a few things that Drake would later come out with the Drake equation, and that it wasn't really, they added a lot of their factors to the Drake equation and kind of made a rare earth equation, which we'll discuss towards the end. And as we can see, with all these extra factors, there's so many more things that can go wrong and lead to life never having existed in the first place. So their book, Rare Earth: Why Complex Life is Uncommon in the Universe, is pretty key to this whole idea, and we're kind of going to use it as a blueprint for this episode and touch on as many points as we can and kind of dig into what they were talking about. We're not going to be super analytical with all their points, but we're just going to talk about it and maybe learn of a few cool things here and there, which is what this podcast is all about. So in the beginning of the book, they list out the key factors that they will later discuss. And I wanted to go ahead and share this list with you. I think this is this is before chapter 1. I have the book right here in front of me, which is pretty awesome. We're just kind of going to go through it. But here are the rare earth factors. Correct distance from a star, right planetary mass, plate tectonics, the right mass of the star, a Jupiter-like neighbor, an ocean, a stable planetary orbit, a Mars, a large moon, the right tilt, atmospheric properties, right kind of galaxy, giant impacts, biological evolution, right position in the galaxy, the right amount of carbon, evolution of oxygen, and wild cards. So those are the key factors, and we're going to get into some of those. One thing to note, though, and the authors do take this into consideration, This is assuming that all life requires the same stuff. Okay. So really, this is if we're looking at life that is pretty similar to Earth, then maybe these conditions are really hard to find, but life could exist in like some crazy form that we don't know. And the rare earth hypothesis would kind of fall apart then. And they recognize this, and that's why it's just a theory. But I do like that they brought that up. And they also actually, their first chapter is geared towards explaining why life could exist in the universe. So chapter 1 is titled "Why Life Might Be Widespread in the Universe," and they talk about how extremophiles, so life forms on Earth that live in really extreme places, like thermal vents, places that are like scalding hot, that we think life couldn't exist. They do exist on Earth. So our idea of what life needs has expanded over the years as we've done more research. So it is possible that that life could exist all over the universe. They say this in the book, but where they have a problem is complex life. They want to distinguish microbial life or maybe single-celled life from complex life, which would be animals or humans or something even smarter and beyond human. They say that complex life probably, according to this hypothesis, doesn't exist, but simple microbial life could exist and be abundant everywhere. And they go into some examples of different types of extremophiles, if I'm pronouncing that right, like ones that live at the very bottom of the ocean, thermal vents, and all sorts of cool stuff. It's really interesting. The chapter 2 is where they start to get into the actual factors. Okay, and chapter 2 is titled "Habitable Zones of the Universe." And I really like this chapter because it talks about something that is pretty well known, the idea of the habitable zone, or HZ, which for people that don't know, I will explain that in a little bit. But not only does it describe what a habitable zone is, it talks about that, or it recognizes that the habitable zone, it's more nuanced than just the simple definition of it, and that it can vary. And so I actually did learn quite a bit from this, even though I was already familiar with the habitable zone. So that was awesome. I really liked this chapter. So habitable zone, what is it? Essentially, it's exactly how it sounds. The habitable zone is an area around a star where life could potentially exist. And that really boils down to a zone within, like, a planet that would exist in the zone is not so far away from the central sun that it orbits that its oceans would boil or evaporate, or not so close that their oceans would boil and evaporate, and not so far that the planet would freeze over, their oceans and their water would freeze. If we look at our own solar system, we have two examples of this. We have Venus, which lies too close to our sun, and Venus is the hottest planet in our solar system. But yeah, it lies just outside of the habitable zone of our sun. And then we have Mars on the opposite end of the spectrum, which lies outside of the habitable zone, but it lies too far away and is far too cold there. Now, Earth, on the other hand, seems to be just right. We lie inside the habitable zone, so we're kind of in the perfect place. And every star has a habitable zone. And this habitable zone is really dependent mostly on the star itself. Okay, so more massive stars are going to have habitable zones that are farther away, whereas smaller stars are going to have habitable zones that are closer. And that just makes sense, right? So if you have a more massive star, it's more powerful, generating way more heat, more radiation, you can't get that close. You got to be farther away. Whereas if you have a weaker star, you have to get closer, otherwise you're going to be way too cold. So this habitable zone, depending on the star, it's going to vary. But the really interesting thing here, and let me make sure I get this date right. What is this man's name? Michael Hart, 1978. He was an astrophysicist, and he discovered that the sun was getting brighter as it aged. And according to the calculations, 4 billion years ago, the sun was 30% dimmer. So from our research of stars and the life cycle of stars, we know that the brightness and its output is not a constant. It changes throughout the star's life. So what does that mean for habitable zone? Yes, the habitable zone also changes. It's not set in stone. So our habitable zone in the solar system is 0.95 to 1.15 AU, which is astronomical units. And for those who don't know, one astronomical unit is equal to 93 million miles, and this is just a unit that astronomers use when we're dealing with huge distances, like in space. And 1 AU is equivalent to the distance from Earth to the Sun, so 93 million miles. And that habitable zone is going to change as our star ages. It's going to get farther and farther away, and eventually we could fall outside of the habitable zone. So when we are looking at other planets that need to be within a habitable zone that we're looking for that could potentially support life, we have to keep in mind that maybe this planet is in the habitable zone now, but was it like a billion years ago? Maybe it doesn't have enough time in the habitable zone to have life evolve to a certain level. That's just another factor that goes into the equation of potential life being out there. Not only does it have to lie in the habitable zone, but it has to be in the habitable zone for a certain length of time. And I really like this because we're starting to narrow it down. Another thing to take note of is more massive stars have shorter lifetimes as well. The lifetime of the star is really important too. Once that star is gone, well, you're kind of out of luck there. So imagine like a really massive star, and of course its habitable zone is pretty far away. We have a planet lying in this habitable zone, and yeah, it not only is the habitable zone going to get even farther and farther, but the star's not going to be around for super long. So to put this in perspective, our sun has a 10 billion year period of stability. I believe after that point, it's going to become a red giant, and its brightness is going to increase by a factor of 10,000. So yeah, it's going to like Earth will just be basically gone. And we're going to have to figure out what to do. But it was not for a while, but at some point we are going to have to figure out what we want to do. And another thing to take in consideration is more massive stars create a lot more ultraviolet, and ultraviolet breaks the bonds of most biological molecules. So maybe it's possible that life isn't really going to exist around a supermassive star because it doesn't have enough time, like we already talked about, and the habitable zone is constantly moving at a faster rate. What about smaller stars? And we know that 95% of stars are less massive than our sun. And the most common type of star in our galaxy are M-type stars, which are 10% as massive as the sun. So now we're on the other end of the spectrum. So our habitable zone is going to be really close to the sun, or to this star. But that might also not be such a good thing. Okay? Being this close to the star adds another level of danger. As a planet gets closer to a star, gravitational tidal effects cause the planet to become tidally locked, meaning the planet would spin on its axis only once per rotation around the star. So basically, like one day, is one day and 1 year are like the same on that planet. So basically, that means that the same side of the planet would always face the sun, and you're gonna have half a planet that is in like eternal daylight, and it's hot as like probably pretty hot depending how close you are, and you're gonna have another half of the planet that is just iced over and in complete darkness. I don't know how conducive that is towards evolving complex life. Probably not that great. Maybe we were just like super lucky to be where we are and to have existed in this spot in our solar system. And maybe if these conditions aren't met, life isn't going to evolve to a complex form. Now, one thing I hadn't thought of that they also discuss in this chapter is the idea of galactic habitable zones. So not only is there a habitable zone for a star, potentially you have to be in the right spot in a galaxy as well. So if you imagine a galaxy, it's really bright in the center. And that's because the population and the density of stars, the amount of stars, goes up a lot the closer and closer and closer you get to the center. That's why it gets so bright. It's because there are a whole lot of stars in there. And the farther out you move, there are less and less stars. So we exist in the Milky Way galaxy, and our solar system is 25,000 light years from the center of the Milky Way. We exist in a part of the galaxy between the spiral arms where the density of other objects like stars is very low. As you move towards the center and you are around more and more stars, there's more things that there are more dangers, right? As you're around more stars, there's going to be higher chances of supernova, stars exploding and dying. And maybe with all these other things happening, the closer and closer you get, like imagine existing in the very middle of a galaxy. There's going to be so much going on there, so many stars, that it might not be possible for life to exist there. Maybe there is a zone in each galaxy that is like the galactic habitable zone, and you have to exist within, this distance. And it's just as nuanced as the habitable zone for a star. There's a lot of things that can potentially play into it, but it's certainly very interesting to think about. Now, if we continue reading, we get to a chapter about plate tectonics. We're not going to get super big into plate tectonics just because I'm not an expert. I'm not an expert on any of this, but I don't really know a lot about plate tectonics except for what I just read in this book. But I mean, you guys know that plate tectonics is basically like the crust of the Earth and its movement, right? A planet that supports life, complex life, potentially needs to have plate tectonics. So maybe every planet out there that doesn't, we can count that out for life in our search. Who knows? But plate tectonics do a few things. They recycle chemicals crucial to keeping the volume of carbon dioxide in our atmosphere stable, which is the single most important mechanism for allowing liquid water to exist on the surface of Earth for the last 4 billion years. So without plate tectonics, we would not have liquid water. So there wouldn't be any life. Okay. Plate tectonics also cause changes in sea levels, which is vital in the formation of minerals that keep the carbon dioxide levels stable. As we just discussed, carbon dioxide levels are extremely important. Also, plate tectonics created the continents, and we would be in ocean world without it, assuming that we had water, because like we said, the CO2, was really, really important to even have water in the first place, but we certainly wouldn't have any continents. And plate tectonics create our magnetic field, which protects us from radiation and solar winds. Those all seem like really important things. Water, protection from radiation, continents, all of those are critical in our evolution. Is it possible for life to evolve on a planet that doesn't have this? We don't know. The rare Earth hypothesis says Probably not. At least from what we know, right? But like I said, I'm not going to get super into plate tectonics just because I don't know. I don't have a lot of knowledge about them. But it's good. I think it's really important for us to touch on it. And I learned a lot just from reading this chapter about it. Another thing, another huge factor in another chapter, the moon. Our moon is special. Our moon is huge. It's nearly a third of the size of Earth. That's not normal. All the other planets in our solar system have pretty small moons relative to the planet's size. The fact that the moon is so big plays a huge role in the way the Earth orbits the sun and the way it tilts, and potentially how life has evolved. And maybe without our moon, maybe a moon that was like smaller, life would not have evolved. And that's what this chapter is about. So we know the moon causes lunar tides, creates tidal bulges, and most interestingly, it stabilizes the tilt of the Earth. So I have a few notes here from the book that I want to give you guys about the moon. So tidal bulges create a force on the moon that cause it to spiral out from its place of origin. If the moon rotated in the same direction as the Earth's spin, we would eventually collide. This will happen to Neptune and its moon Triton. Okay, so you're either going to have a moon that is spinning in the direction of that is spinning in the direction of your orbit, or you're going to have a moon that's spinning in the opposite direction. So I don't know what the odds are of getting. I don't know if anyone knows what the odds are, if it's more likely for it to spin in one direction or the other. But I mean, you got two options, and if one of them, if it's spinning in the same direction, you're screwed because the moon is gonna crash into you, and that's probably gonna put a damper on any life that's evolving on that planet, right? Especially depending on how big the moon is. If our moon crashed into us, like, that's an apocalyptic event. So we should be thankful that it's going in the opposite direction. Another super important thing our moon does is it stabilizes the tilt of the Earth. So Mars, in comparison, has extremely small moons, and researchers believe that the tilt of Mars has changed 45 degrees or even more throughout its history. Now, why is that important? Well, the tilt of our planet is what's responsible for our climate. It's responsible for our seasons. Okay, so this kind of thing is a little hard to describe over kind of just audio form. This is best seen through visuals. So if you guys have a chance, definitely like go on YouTube and look for maybe some sort of explanation or diagram of how like the tilts and how the tilt works and like what it looks like. But essentially, you're going to have one hemisphere for half the year is going to be getting more sunlight due to the tilt, and then the other half of the year, the other hemisphere is going to be getting more sunlight. Okay, so that's why it's, winter in the north, but summer in the south, and vice versa. So it's responsible for our seasons and responsible for our climate. We can take extreme examples to see how that would affect climate and seasons. Just in our solar system alone, we have some pretty good examples. So Mercury, for example, has no tilt. It's like straight up, and it has no seasons at all. It is hot there all the time. It not only Mercury is a hellhole. It's not as hot as Venus, surprisingly, even though it's closer to the sun. But that's just due to Venus having the atmosphere that it does. It traps all that heat. But yeah, Mercury is not a good place to visit. Uranus, on the other hand, is kind of the opposite of Mercury, but its tilt is at 90 degrees. So it's at the other end of the spectrum. And this is really bad too, because the 90-degree tilt causes one pole, like north or south pole, one of the poles will be exposed to the sun for half the year, while the other is in complete darkness. Yeah, I really like this chapter because it explains all these processes, and I definitely feel like I learned a lot by reading this. And I don't know if this is in the same chapter or the next chapter, but it also talks about Jupiter. Jupiter is the largest planet in our solar system, right? It is 10 times larger than the Earth and 300 times its mass. And maybe having a planet like Jupiter is essential to having life evolve. We think that throughout our solar system's history, Jupiter, with its massive gravitation force, because it's so large and so massive, has scattered stray objects flying through our solar system that could be a potential hazard, so like giant asteroids and stuff like that. So maybe Jupiter is kind of like a silent protector, watchful guardian, and it's protected us from who knows what over billions of years. Maybe a planet that doesn't have something like that is more likely to keep getting extinction events. And they get these events at a higher rate, and life just can't evolve. Something to think about. So, another huge factor is the spark of life. Okay. So, we know that life on Earth needs water, needs carbon, needs these elements, right? But so far, our best attempts at creating like a soup with all the ingredients has not just, it doesn't seem that life just spontaneously appears. We don't know what causes life. We don't know what creates DNA out of just elements. And that's kind of that's a question that needs to be solved, and I don't know if we ever will solve it, because right now there's kind of something just mysterious about life. And I mean, that's exciting because there's something that we can learn, but gosh, I really want to know. And it's, if we kind of think about this in the sense of the rare earth, maybe whatever causes life to spark only happens on Earth for whatever reason. We can't really say it because we don't know, but maybe it is extremely rare. And they have a whole chapter talking about this. It was interesting, but I don't think it was quite as good as the other chapters, because basically it was just like, we don't know. But you have to take it in consideration. So in one of the last chapters, they talk about the Drake equation, which we've gone over in one of our previous episodes. And they essentially want to build on this equation and add their factors to make it the equation more complete, right? So the original Drake equation, I guess I should explain to people that are listening to the first time what the Drake equation is. But essentially, the Drake equation is an equation created by an astronomer, Drake, back in, I believe, the 60s-ish. And its purpose is to estimate the amount of intelligent civilizations out there in the Milky Way galaxy. And the simplified version of the equation, because it is a mouthful, it's basically, but bear with me here, stars in the Milky Way galaxy times the fraction of sun-like stars times the fraction of stars with planets times planets in a star's habitable zone times fraction of habitable planets where life does arise times fraction of planets inhabited by intelligent beings times percentage of a lifetime of a planet that is marked by the presence of a communicative civilization. Okay, so there's a lot of factors there. And we got to keep in mind with this equation that if even one of these factors is zero, then the equation equals zero. And that would mean that there are no civilizations out there. So what the authors of this book, the authors of Rare Earth, propose are a few more factors that we need to add in to make this equation even better. And what they do is they create what they call the Rare Earth equation. And the Rare Earth equation is stars in the Milky Way galaxy times the fraction of stars with planets times the fraction of metal-rich planets times the planets in a star's habitable zone times stars in a galactic habitable zone. All right, so we got a couple of our factors that we talked about in here. Times the fraction of habitable planets where life does arise, times the fraction of planets with life where complex metazoans arrive, times the percentage of a lifetime of a planet that is marked by the presence of complex metazoans, times the fraction of planets with a large moon, times the fraction of solar systems with Jupiter-sized planets, times the fraction of planets with a critically low number of mass extinction events. So they added all their factors from the book, which we didn't go over all of them, but they added it into the equation. And as you can see, with more factors, there's more potential for one of these to equal 0 and then set the outcome to 0. And the outcome, of course, is how many intelligent civilizations are out there. So all in all, I really like this book a lot. I read the whole thing, and I highly recommend you guys checking it out. It's a good read. It is a bit dated. This book came out in 2000, so bear that in mind. There's been more research since then, and some of the stuff, it could definitely use an update, and I really hope that they potentially release a sequel or a follow-up, or maybe a second edition or something like that. That would be really interesting to see. Now, the rare earth hypothesis has received some criticism, and I think it's important that we talk about that a little bit too. But honestly, the criticism is, I'm not going to say unfounded, but it's the authors knew this and they were aware of it, right? So one of the top criticisms is that the rare earth hypothesis is assuming that life elsewhere in the universe is going to be very similar to life on Earth. They already talked about this in the book, so I don't even really know how that's criticism. Like, obviously, yeah. But life on Earth is the only thing we have to go off of, so the authors recognize that, they talk about it, and but you got to keep going, right? You gotta just accept that and take note of it, but you got to keep going. You can't just get caught up in that. So I wouldn't say that's criticism technically, but a lot of people will bring that up when you talk about this. So we got to address it. There's also not a lot of research about, at least at the time, from anything that I could find, there's not a whole lot of research that shows that Jupiter has been essential, right? We can guess. It's kind of it seems like Jupiter would be pretty important because of its huge effect in the solar system, but there's nothing saying for sure that all these asteroids that would have hit Earth have been, in fact, been deflected. We're kind of just guessing, you know what I mean? It's just a theory, though. They're not stating this as a fact, but it is important to think about. We don't have any way really of knowing how many asteroids Jupiter has saved us from, so it's just a guess. That's okay though. I'm still for it. Why not? I'm curious as to what everyone else thinks about this. So that was pretty much the book. We went over a lot of the factors. We left some out just for the sake of time. And overall, I think it's really good. My personal view on it, though, is I'm not necessarily, like I said in the beginning, I'm not really 100% buying into this. Because of the quote unquote criticisms, right? Like, those are valid points. But I mean, I have to admit, the rare earth hypothesis, it kind of fits what we see. Like, you know what I mean? Like, it seems almost one of the, as pessimistic as it is, and as much as I don't want to believe it, it fits a little, it seems more realistic than some of the other ideas that we've discussed on the show. The zoo hypothesis, like, potentially that could be true, right? We're just surrounded by like some sort of hologram or screen or planetarium, and the aliens only want us to see that the universe is empty. Like, I get that could be real, but like, I don't know. It still feels kind of fantastical, right? This idea seems a lot more based in reality and based on observation. And as much as I don't want to say that it's not real, I'm torn. That I really think that this could be accurate, and that I don't know how I feel about that because us being alone is pretty scary. But we have nothing to go off of, and all our efforts have showed us to be alone. So maybe I'm not going to say I'm a proponent for the rare earth, but I definitely think that it is a solid theory, and I think it's going to be relevant for a very long time until we find something crazy that will completely alter the way we look at astrobiology and life in the universe. We have to really consider this to be a scenario that is true, that could be true. And the thing with Earth's history, there could be so many other factors as well that aren't addressed here that it like the list of things that we need could be just astronomical. The list of events that needed to happen for us to get where we are, it could be like you can't even count them all. Maybe everything was just so perfect. Who knows? And I did leave out a factor that that I wanted to touch on briefly. I don't remember what chapter it's in, but a planet with life, with intelligent life, might need an equivalent of Mars next to it. And basically, it would need another Earth-like planet that could potentially support life. So Mars, at one point in its history, could have potentially supported life because it did exist in the habitable zone. So if you have two planets within a habitable zone, maybe one planet can seed the other. Maybe, well, that would increase your chances of life, right? So it's possible that that could potentially be a factor that we need to look at, is maybe multiple planets in a habitable zone increases the chances. I just wanted to throw that in there because I forgot about it earlier. Yeah, but I want you guys to let me know what you think. Is this idea something you can get behind? Do you think this is true, or do you think that that extraterrestrials do exist? Do you think that they're visiting us right now, or do you think maybe they have visited us in the past? Which hypothesis really speaks to you? Let me know. I think in a future episode, we're going to look at the idea that extraterrestrials exist, but they are really far away, or we haven't discovered them yet for whatever reason. And there's a lot of cool ideas that we can talk about there, like cosmic distances and how long it takes to travel between stars and radio signals and all sorts of stuff, because there's a bunch of reasons why they could exist, but we just wouldn't know about each other. And I think that would be a really good idea of an episode. So if you're interested in that, stay tuned. That'll be coming out probably within a week or two, depending on how long it takes me to work on these. Some of these episodes take longer than others, just because of like the research I have to do, or I might have to read like a book. But I have other stuff coming out here and there to keep you guys occupied between these episodes. I want to thank you guys for listening. And I really appreciate you guys tuning in and giving me feedback and helping me build this community up. It's pretty crazy. Anyone who's listened to this and followed me like on TikTok, hopefully we hit 1K today. So I don't know why TikTok of all things is blowing up. I really wish my YouTube channel would blow up, or like my podcast. But hey, maybe people from there will like come here and listen to this, and I don't know. So I'm trying to cast a very large net and grab people from everywhere and hopefully build like a pretty solid community eventually. But yeah, if you're here right now listening to the beginning of this whole adventure, I appreciate it. You guys are great. Hopefully these shows only continue to improve as I get better at this. And I think the most important thing is that we just have fun at the end of the day. But yeah, you guys go ahead, keep an eye out for other stuff that I have coming out this week. Follow me on all the normal stuff, TikTok, Instagram, blah, blah, blah. You guys know the drill. And I will catch you guys on the next episode. I hope you've enjoyed this week's episode. Remember to raise your telescopes and never stop on your quest for knowledge, except for maybe a drink. This is The Bar at the Edge of the Universe. I've been your host, Adrian Maddox. Thank you, and good night.